There's a two-line proof of this using Chebyshev's inequality. See, what this means is the probability that yn bar, let's call this yn bar, the sample average, minus the expected value of y, less than or equal to epsilon, goes to 1 as n tends to infinity. And this is called convergence in probability. That is, the probability your epsilon away goes to 0. The simple proof of that is just square both sides. It's the probability this square is less than that. Then calculate the expected value of the square, which turns out to be n times the variance. And then use Markov's inequality that says the probability that a positive random variable, and the square of this is positive, is greater than or equal to t times its mean, is less than or equal to 1 over t. All right. So I think the text runs through that quickly. So this is a slightly weaker statement than convergence with probability 1. But actually, as much as I like statements like this, these will suffice for everything we wish to prove this quarter. That is, convergence in probability will be sufficient. Okay. Now I ask, what about a product? Let yi be greater than or equal to 0, yi IID sequence, and let's take the product of yi from I equals 1 to n. How does it behave? Well, the reason I made it positive is so this wouldn't be flipping signs. Okay? Well, if I put a constant in here, a, then the sum grows linearly and we should divide by n. If I put a constant in here, a, then the product should go like a to the n. So the way to sort of normalize it would be to take the nth root. So the question would be, how does this behave? Well, the first attempt at this is expected value of the product of yi from 1 to n is the product of the expected value of yi, I equals 1 to n, which is the expected value of y to the nth power. See, the expected value of the product of IID, independent random variables, is the product of the expected values. But this is misleading. Because this product is not going to be equal to this with high probability. And in fact, this product behaves like something else. In case this would be one of the first fallacies of investment. You try to maximize your expected return on each investment, and you think that that's going to make life good. Well, the problem is let's take yi, now say equals 2 with probability a half, and 0 with probability a half. So you either double your money or you lose it all. So then this product would go like this. 1, 2, 4, 8, and then 0. In other words, this product will eventually be 0, and it'll stay 0 forever. So a person who maximizes his expected return is probably overbetting his capital, and the low values this can take on will swamp out the frequent high values, and you're dead. So what really does characterize the behavior of this product? Well, we can do this. Product of yi from I equals 1 to n, nth root. It'd be like a to the n, nth root, back to a again. In other words, it's the growth rate of wealth. So we ask what that is. Now, let's go back here and look at product of yi. Well, yi is e to the log yi. That's an identity. And then the product adds in the exponent, so that's e to the summation of log yi. Now if we take the nth root here, the nth root comes in here. And now this quantity I know converges in probability to the expected value of the random variable. So this converges to the expected value of log y. So this whole thing goes to e to the expected value of log y. Notice up here the expected value of log y is minus infinity. So and e to the minus infinity is 0. So you get the right answer. And because this is close to its expected value, then this will be close to e to the expected value of log y. So that's how products behave. It's essentially a law of large numbers for products, is that the product behaves like the geometric mean. This is geometric mean. Let's say y equals a half the time and b half the time. Then e to the expected value of log y will equal square root of a times b. Just check it out. And this, of course, is the geometric mean of a and b. And there's an inequality the relationship of the geometric mean to the arithmetic mean. Geometric mean is less than the arithmetic mean. And really what that means is this is doubly misleading, because if we put the arithmetic mean to the nth power here, rather than the geometric mean to the nth power, we have a much higher expected, this time not expectation, but just we think that this would grow faster than it actually does, because the arithmetic mean is higher. There's substantial controversy in the finance literature of what you should, how you should invest. And much of the theory says maximize the mean. Oh, that doesn't give you a diversified portfolio. It means bet on this stock. So let's try to minimize, maximize the mean minus a variance term, or something on the so-called efficient frontier. Again, mean and variance have nothing to do with the product, except when the deviations from one are very, very small, in which case it's a good approximation. So, my strong feeling is that one should maximize the expected log of your wealth, and that will give you your maximum growth rate for your exponentially increasing wealth. But as obvious as that is, it's not necessarily the orthodoxy for investment. Why? Well, because of this unfortunate fact. See, this is expected value of log of your wealth. Aha. Log of wealth might be a utility function. And that would mean this is just another utility function. Look, somebody who makes 6-figure salary or an 8-figure salary is probably like somebody who makes a 7-figure salary. In other words, the half-half of the log would be a good way to judge the utility for money. So, in any case, if you go, you could fool yourself into thinking that, oh, expected logarithm instead of expected value. Well, logarithm means I have a utility for wealth, which is the log. And before you can go one step further, they say, wait a minute, that's just another utility function. I would say, wait a minute, the path I'm taking is growth optimality. How much can you generate with probability 1? And you could call it a utility if you wish. Okay, now we're set up to look at the asymptotic equipartition property, AEP. So let the xi's be our IID drawn according to P of X. And we're going to claim that minus 1 over n